Thank you a lot for the kind invitation and sorry for not being physically there. So my talk is indeed that we need to, I think, balance proprietary IP and open source to build robots like, for example, Baymax. And so when the academic opening was by our rector, he already mentioned the importance of science as a public good. And also, we think that robots are a big enabler for the UN Sustainable Development Goals. But of course, there are also disabling factors. And for that, we wrote a paper, and we are also now submitted a bigger paper on the roles of robotics in achieving these UN Sustainable Development Goals. And how we can reach them. So from our funders, it's of course important to publish open source, green or gold. But yeah, is that enough to have real impact and to really have robots doing the jobs in our society and environments for those common good? And we think it's an important tool, but of course not a sufficient tool. And I think talking about open source is really important. And for example, when there was a corona, we, for example, saw that in the hospitals, there were a lot of filters available that were not used anymore. And we turned a Decathlon snorkeling mask with an adapter that we open source released with the help of a lot of doctors. And so with the help of, for example, BIC, who did the mass production of that, more than half of the Belgian university hospitals got them for free, which even led to cartoons in the newspapers. And also in our Fab Lab, and our researchers contributed to Vrije, which was an open source breeding machine. And so to go back to robotics, a long time ago, we developed this social robot Probo, which had 20 motors in the head to show different facial expressions. And we had a European project Dream on how we could help children with autism in order to learn social behaviors. But of course, it used Maxon motors. It was an expensive platform, and only one prototype was built. So we thought how we could have impact. And so Jelle Saldin, who was the lead researcher here, became professor in the University of Ghent. And there he developed Ono, which was an open source, much cheaper platform. And even when it became cheaper and even more accessible with the Obsoro platform, also showing different facial expressions with really very easily, very ingenious tools to assemble different types of robots. And he also wanted to develop a company out of it in order to serve that community. But only with open source, we think that it's not such an easy thing to do. Because yeah, investors are really not so keen on that model alone. And so, of course, there are examples like Arduino, several open source printers, some drones, and so on. But I think that, yeah, to have a successful company, I think you at least need to have some strong patents that the investors want to invest in. And so, for example, we have our Axelis Bionics startup company from our lab, which now recently launched the first product. It's a very challenging product because it's a medical product. So you need to have all the certification. And so on the basis are patents. And yeah, to do it completely open source, I doubt if people will go on the website and be able to assemble their own prosthesis, especially for lower limb prosthesis. So I think in order to impact the society, you need a spin-off company or start a company in order to build and provide this technology. People think, yeah, when we have patents, we cannot publish anymore, which is not the case. Only you need to take care of the timing. And so we extensively publish and also are still publishing on the results of this technology. At the moment, we're also pitching a new company for occupational exoskeletons and also a very new gearing technology, which drastically improves the energy efficiency because as such we can create much lighter robots because a lot of energy is lost only over the gearing. And we rethought this concept, and we also want to go to a company around this technology, which we also patented. In order to go back to soft robots and Baymax, we also, Alex showed you this nice video where Baymax got hurt during his adventures, and he uses the tape in a police station to repair it. But soft robots are, of course, very vulnerable. And for example, this universal gripper, after 50,000 grips without sharp objects and only after 5,000 grips with sharp objects, the material already is damaged, so we cannot use it. And so 50,000 grabs sounds a lot, but it's really not. It's, I think, a day of work in a company, and that of course makes that it's not, you need to or costly repairs, or it ends up on the e-waste pile. And so this is not economically and ecologically feasible. And that's why we started to make sustainable materials, and we rethought the whole cycle around it. So we made soft grippers, and if out of self-healing materials. So that means if there is damage, you can extend the lifetime by healing it back into a healed finger, which can of course have the original functionality back without loss of mechanical properties. If the damage is too big or it's not needed, that part anymore, then we can mechanically recycle it. And that's a very new thing for network polymers. Those network polymers have big challenges to be recycled. That's why you cannot recycle tires, for example, from a car. But our material you can completely mechanically recycle. So for example, you can print it again, but also chemically recycle. So you can go back to the original monomers and give new material properties to the material. Moreover, we're looking to renewable resources and also biodegradation. So that means when the material is released in the nature, it biodegrades. So you see sustainability on different cycles happening. And in order to realize this, you need to have breakthroughs on the complete value chain. So in our group, which has more than 20 persons only working on the self-healing, we have researchers working on the self-healing polymers. So we have a whole portfolio of materials, so we can make them very soft and very hard, very rigid, and we can also heal them together. And you see when you do tensile test, you see that it breaks in the weakest material and not at the interface, because usually when you make multi-material components, the interface of the material is the weakest component, which is here not the case anymore. So then we also study different manufacturing techniques. Often we use 3D printed, but if you want to go to larger quantities, you can also go to molding. And it's even possible to combine different manufacturing techniques. We not only made non-conductive materials, we also added fillers, magnetic or carbon black and so on to make it conductive. So we can use it as a sensing element, but also as a heater, on which I will come back later. Moreover, it's also the same self-healing material, so also the sensing element itself can be healed, damaged and be healed. And then, of course, we can make different robotic components out of it. And one of the patented materials is to be able to do room temperature healing. So typically, self-healing materials, when you want to heal fast, they have very weak mechanical bonds. And that means also that your material is not so strong. So we thought how we can combine both very fast healing with very good mechanical properties, which are needed to make structural elements of robots, like, for example, the grippers. And here you see that we damaged the material, and you see the scar being, the damage being healed. And because at the inside of the finger, the healing is fast enough, and you see we damaged it a lot, and you see scars completely over the finger due to not completely proper alignment, but it's enough to restart working. If you completely cut the finger in two, we need here 7 days at room temperature to heal, but in the meantime, we were already able to bring this number down. So I mentioned we could also add fillers, and then of course, we can make different types of, the sensors that we all know when using non-healing material. So we can make strain sensors of it, capacitor sensors, and it is of course the big innovation that you can damage the sensor and heal it back together, so it can restart to work. So we can also use that also as a damage detection. And so we have room temperature healing, but that of course means that we don't have control on the conditions on when the healing takes place. And so you damage it, and that's the stimuli in order to start healing. But imagine that the finger is working in a dirty condition. Yeah, then of course you first need to clean, otherwise all the dirt is also in the wound, which is of course not desired. So that's why we also go to non-autonomous healing, where we need a trigger, and for us it's often heat in order to start the healing process. So that means you can control the conditions. Hey, for example, there is damage, you can detect how severely it damages, and you decide, okay, I need to put it down, and then I need to clean, and then I start the healing procedure. And because we have that conductive material, hey, we place the finger back together after damage, we send a current through, and that generates heat, which is sufficient to heal it, and of course, then bring it back to action. So we have a complete system where the healing is embedded with non-autonomous healing material. And then we can make nice things with it. So this is not yet a published paper, it's under review. So we make voxels, so we make very stiff voxels, we make compliant voxels, we make active voxels, so which it's an inflatable cube. And then, we can assemble it, we can heal it together. And for example, now it is a gripper that we developed. But then we can completely cut apart the gripper apart. We can reassemble the parts, and then, for example, we can create a walking robot with it. And so all the different cubes are here together, and because we have different material properties, but still the same chemical bonds, at the interface, there is a perfect interface there. The challenge is, of course, those are patented materials, but of course, we can make a huge amount of applications out of it, but these are, of course, outside the reach of our own capabilities. For example, we want a punio gripper. We saw that there were some damages. How can we maybe make this punio gripper out of self-healing material? And that's why we started to develop also a tutorial how to use those self-healing materials. And so we provide all the steps, the molds, the software, and so on, in order to make your own self-healing gripper with an embedded sensor in it. So we organized in the European project, which I coordinate, a SMART project, we organized different training events. And so during the winter school in Cambridge, we showed for the first time this tutorial. And so you see all the different steps, how to take the bubbles out. Here is, for example, embedding the sensor in it, adding the self-healing material in the mold. So the nice thing is also when you have still some holes, you can later add self-healing material, and due to the strong interface between the different parts, it heals perfectly together. We made a box for a servo motor. We wanted all the materials very cheap in it. And then we have also the software, and then we can show what happens when you cut it. You can see the damage, and then you can bring the part back together in order to start here the healing procedure. One of the things is that we can do the tutorial with our self-healing material. But a few weeks ago, we also did a workshop at the science fair where we used non-self-healing material. And I think we made over 300 fingers with this procedure in order to inspire children also on self-healing soft robots. We also use SOFA a lot, which is an open source framework to model soft robots, where we also just on the Robotics and Automation magazine, and I think it's already available as e-print, a tutorial how to start a SOFA and to make a soft robotic finger out of it, but especially how the properties of the material are embedded in this SOFA framework, and how properties of the material impact the behavior of the finger in this case. And because we want that we have a certain behavior desired, so that is determined by the design of course, for example, the finger, but also which materials are embedded in it. And so we can both modify design, but also modify the mechanical properties of the materials. And so those are the parameters we can tune in order to have a certain behavior. And this is a tutorial which we released on this matter. So the idea is to go to fully autonomous self-healing soft robots. And so we need to do damage detection with embedded sensors in it. We also have embodied intelligent design. So we're going to multi-material designs. So also our hands are designed with a lot of materials in it, from bones, fat, nails, and so on, and how we can model that. So we mostly use SOFA, but also other modeling software, so how we can do the smart motion control. And in order to have that design, how we can tune the network, and we have a lot of parameters in it, had to change different properties in that material with the embedded sensors in it. So I think open source is a very important tool, but I think when we want to go to commercialization, exploitation of it, I think we need a very balanced IP management in it, which is on one hand having patents on it. So we have patents on our self-healing technologies. How we do also security-based control, that not everything we put in patents, but some things, it's in software, and what we release open source in order to have a wide range of application possibles with our sustainable self-healing technology. So thank you for your interest. And so indeed, it's based on several European projects, which I coordinate. So Shiro will end in November, so it's a few more days. Then we have still the smart network, and we still do also completely free training events on using smart materials for soft robots. And now we also have a new project, Shinto, which started 1 month ago in order to further mature this technology. And it's a very strong collaboration with our robotics group, but also FISC, which is the polymer research group. And I think this multidisciplinary approach is very important for soft robots. So thank you. Are there questions?
We can have a couple of questions from audience.
I have a question. Where can I find more information about the additive manufacturing?
So I think the question was to have more information on the additive manufacturing.
Yes.
So yeah, so typically you need thermoplasts in order to have additive manufacturing, because you need to melt the material in order to have additive manufacturing. And so typically network polymers, so you have the polymer chains they have crosslinks, and that allows to give very interesting properties to the material, but also allows that you cannot go to a flow behavior anymore, which is needed for 3D printing. And so that's typically the reason why those network polymers, you cannot do additive manufacturing. And also that's the reason why you cannot recycle them, because you can heat it up, but that after a while it burns and not goes to a flow behavior. But the innovation we have in our material is that you have the polymer chains and the crosslinks, but they have reversible bonds. So that means you can open and close them. So that means if you cut them, you get on those reversible bonds. So you open them, and when you bring back the material together, they reform and they bind again together. And that means that the network is healed again. So if we heat up the material, we that also makes that we will make some bonds loose. And if we don't increase the temperature too much, then we still have the structural integrity of the system to heal, to have higher mobility. So it's higher that those bonds meet each other and heal the material. But if you still increase the temperature, then almost all bonds will break. And that means that you will have a flow behavior. And that means that then you can, for example, start to make a 3D print. The big difference with thermoplast is when you typically print a material in the Z-axis, and when you print layer by layer, the material is weaker in this direction, and then when you have the filament that you have in the other direction. So you create anisotropy in your material, but because here we have reactive printing, because when the material comes out of the nozzle, there is a chemical reaction taking place. That means that the material is covalently bounding also in the Z-axis, meaning that you create very strong mechanical chemical bonds, and that means that also we have anisotropy in our material, so it's as strong in all directions. Moreover, for thinner material, it's much stronger. And so, but we're still working on it, that we can have multiple nozzles in order to mix different materials together, because imagine you can have different properties of the material, having stiff material, very soft material. You can add fillers. And so the idea is to create printers where we can print like that voxel-based concept, where we have made at the moment cubes. But the idea is to go to a smaller scale, that you can have different materials printed together. And because the interface is so strong, we can completely mix all those different materials. But so that's the longer term vision of this additive manufacturing route, which has unique capabilities due to the material being the self-healing property, but also the multi-material bounding, which I think is also very important.
Thank you so much for all that info.
Thank you.